This program was brought to you by Koller Institute of Venture at Tel Aviv University.
Thank you very much, and thank you, Uri, for your introduction, which was very useful and will help me with mine. Will save a little time because the problem, the size of the problem was very clearly presented. I apologize that for some reason I don't appear in my CV doesn't appear in this book, so don't try to.
It was too large for the book. Too large for the book.
Okay. I would also say that I think this brain school or neuroscience school that we just established was one of the best things that happened in the university in the last few years. Well, let's see if we can move this forward. And if we can, so I'm a brain researcher, and as my expertise is in signal processing, I'm actually studying the signal processing capabilities of animals, and each one of these animals has capabilities that are far better than any computer can do. Okay, this little sonar bat, there are about 800 species of this type, does calculations in real time with the number of neurons that's much less than the number of transistors in a Pentium of the previous generation. The energy consumption is few millworms a day, and the calculations that it does, if you hook a cloud, Amazon cloud, to an electric station, you will still not be able to do the accuracy that this animal does. The dolphin has an ultrasound that's far better than the ultrasound that we are trying to create or that we are able to create. And the elephant I'll get to later. This does the same under the ground. So these are amazing animals, and I've been spending a lot of time trying to understand the signal processing that they do. And now I flip the page, and I'm trying to use advanced signal processing to read the brain. Okay, so my mission is very, very simple. I want to do what the glucometer and the adrenaline pump did to diabetes. I want to do that to the brain. Okay, so the glucometer really enables us to see when there's a problem, when we cannot, when we do not have enough glucose in our body, and then the adrenaline pump can release the medication very easily. Unfortunately, we cannot look into the brain. This is still 2014. This is the way we look into the brain, and I want to look into the brain with something much, much smaller and be able to say much more than can be said with looking with many electrodes. So in the medical field, it is very clear what I want to do. I want to try and reduce the big machines that are definitely not mobile and also very expensive. And in the consumer market, I want this to become a lifestyle, very useful lifestyle product that can help us enjoy things more, can help us communicate better, and be something like the cardiac meter, the polar meter is helping us training and do physical activity. And these pictures are not here by chance. These are all potential strategic partners for this product. So the future technology, and we saw this picture, this is also electronics. This is very, very flat electronics, so flat and so small, then it can really fit and not be seen at all and sit on our forehead. And I'm trying to develop technology to that day when this technology, when this sensor becomes available, and this is very few years from now. That's a big company that's receiving a lot of money from the US Army to develop this technology. And I want to see what I can do in terms of signal processing with the signal that this device will be reading. That's the basic idea. So as I mentioned, the current problem is that we cannot really read the brain. We can read, every other organ in our body, but the brain, the most important organ, we cannot read. We definitely cannot read it continuously and not at home. So I think that's part of the big problem that Uri mentioned before. That's why we don't really have cure to a lot of diseases. I'm going to skip history, and I'm going to go to our days. The most advanced signal processing technique which is wavelets and variants of wavelets. I'm not going to go into them. Were devised for what? Here's a quiz. For detection of seismic activity. Basically, seismic activity is extremely complicated signal, and as you well know, we cannot detect earthquakes still. If you think of it, it's the same problem, isn't it? The head is a little bigger. Okay, it's like the whole the whole Earth. The seismic sensors are similar to the EEG sensors, and we are trying to detect something that happens in the center or under the ground with sensors that lie outside. And I did take this connection and am trying also to detect earthquakes with some nice success, but I'm not going to go into this here. The reason why our friend the elephant is here is because this elephant is doing better than our signal processing, and these elephants have seismic sensors in their legs that enable them to detect earthquakes before we can detect them. So that's really, I'm not going to get into the complicated signal processing that I'm using, but it's very easy to explain what it is that I'm trying to do, because each one of you can do it. We can sit at a Philharmonic orchestra room, very far from the orchestra, close two eyes, close one ear, and with the one ear that we have, be able to distinguish between the violin and the trumpet playing in the orchestra, although they play kind of at the same spectral bandwidth. And the reason we can do that is because we say that the sound has color. So the violin is warm and the trumpet is metallic, and people with better hearing, like conductors, can really decompose the whole orchestra as it plays and can distinguish between a Steinway, a Stradivarius violin and a regular violin and a Steinway piano, etc., etc. That's really what I'm trying to do with the EEG signal. So rather than putting a lot of microphones next to each of these instruments, I want to put one microphone and listen to the whole orchestra. This is what we can do with our ears. I want to do the same with the EEG signal. So basically, different regions in the brain have their own kind of color of activity, okay? And the idea is to have one or two electrodes in the forehead of the brain and distinguish this color of activity. This is, by the way, a very difficult signal processing task. We don't know how to do it, although each one of us solves this. And this is the kind of pictures that I get. So here, think of this as 120 musical instruments in the orchestra, okay? And the color represents the activity of one of those musical instruments, and then think of those musical instruments as a functional brain region, and I can read that region and I can say a lot about them. This is a slide representing the 3 stages of sleep in a way that cannot be seen in any other way. This is the entrance to sleep, which is very similar to meditation. This is kind of dreams. We'll see soon how it looks like movie watching. And this is deep sleep. This is the only time that the conductor leaves the orchestra. If we look at another way of entering into sleep, we can see something here called hypersynchronization. We can see a lot of beautiful, amazing pictures like this, and I apologize, some people find it overwhelming, but look, think of this as specific regions of the brain active, and really I can see when they're active, when they're not active. I can study these patterns. Emotions is considered to be one of the most difficult tasks of reading in the brain, and if we could tell something about emotions, we would be very, very happy. These are deeper regions in the brain, so they are not considered to be able to be read with many electrodes, definitely not with 2 electrodes. Here, the first part is a frightening movie. This is a happy movie, starting happy, becoming sad, starting sad, becoming happy. Same region of activity of happiness. Repeats itself in meditation, repeats itself in the beginning of sleep. Very interesting. There's no other way to see this. This is the funny slide, but a very important one. This is the person falling asleep while watching a movie. And what you see here is those parts where that person, which is, by the way, not completely falling asleep, is still connected with the movie. As you can see, these paths here represent emotional connection with the movie. So you see the emotional connection here. You see here partially falling asleep. You see this kind of water coming down. However, you can still see in the background that the person is still connected with the movie. Here, you see it even longer. The person is still connected with the movie. So imagine what you can say if you could really measure the ability of people to remain alert. These people are still connected. I'm actually doing this experiment all the time in my class. When I see a student that's kind of falling asleep, I'm asking them a question, and most of the time they answer. So they show me that while they are partially falling asleep, they are still connected. And of course, we would like to know that our pilots are not in this condition. Something that was done outside of the university recently, what can show the applicability of this to neuromarketing, which is kind of where people are mostly interested. I'm going to have to go very fast through this. One slide, this is a person that was fast asleep for the first 14 minutes, 70-year-old female, fast asleep at the first 14 minutes of the NCIS episode, and at this point became very, very emotionally engaged with the episode, sleep, switch to emotional engagement with the episodes. I'm going to skip those. I'm going to just concentrate on one line here, and this will be 3 slides before the end. The basic idea is that I can show emotional engagement or any other engagement of a group of people very easily, very easy to collect the data. I can show at a resolution of 1 second, I can demonstrate how people are engaged with the movie and with the advertisements. Here you can see something that they do towards the end of an episode. They increase the tension in the episode, and so that people will survive the advertisement period and then go to the next period. You can see that at the beginning they were more engaged, and then towards the end, and few episodes in the middle. Some competitors, there are many competitors. These are all competitors with many electrodes. None of them is actually showing what it is that we can show now. Most importantly is Nielsen, who bought Neurofocus for $1.1 billion. Nielsen is the biggest advertisement company, so that kind of gives you an idea about the price of these things. These are kind of toys, but nicely designed. They don't have any ability to measure very serious. They all rely on old, like 90-year technology of EEG monitoring, because this is really what everyone is ready with. And if we are talking about deep innovation, the way I see deep innovation is if you have an idea and everybody says it's impossible to do, no one has done it, forget about it. Or if they are less polite, you know, they would use other terms. But that's deep innovation. If you then can show that you can do it when everyone thought there's no way, this is what we are. So to summarize, a vast opportunity. I want to put a mirror in front of our brain and let us read our brain continuously all the time for a vast number of different applications. Thank you very much.
This program was brought to you by Koller Institute of Venture at Tel Aviv University.